Okay, everybody, I'm going to try to walk you through several of these problems here. Hopefully I can get them all out to you today. But anyway, let's get started here. The very first problem, again, you should have worked these out by now and tried them out. So, again, stop the video, try them, restart the video. Okay, our first problem. The mean price of a house in a certain neighborhood is $51,000. The standard deviation is 8,000. Assume the distribution is approximately bell-shaped. It's approximately bell-shaped, and we want to find the price range for which approximately 99.7% of the houses will sell. So basically what we're looking at is we want a price range, we want an interval where 99.7% of the data lies between these 2 points. The key word here is it's approximately bell-shaped. That indicates we want to use the empirical rule, the empirical rule table. That's what we're going to work with here. And so what we need to know is, well, what we know from the empirical rule is that 99.7% of all data lies within 3 standard deviations of the mean. Okay? Within 3 standard deviations of the mean, which is 51,000. So all we have to do is take sigma, multiply it to 3, and you get 24,000. Over here, minus 24,000, right? From the mean. So if you add 24,000 to the mean, you're going to get 75,000. If you subtract 24,000 from the mean, you're going to get 27,000. So this is an interval that contains 99.7% of the data. Remember, the empirical rule is a table, and it tells you for 1 standard deviation, 90% of the data is in between within 1 standard deviation of the mean. 2 standard deviations is 95%, and then 3 standard deviations, 99.7% of the data is within 3 standard deviations, okay? So, the empirical rule, but the key word here was bell-shaped. Second problem, the mean price of a house in a certain neighborhood is $51,000 and the standard deviation is 8,000. We want to know what minimum percentage of houses are priced between 35,000 and 67,000. So we're trying to determine what percentage of homes have a price between 35,000 and 67,000. All right? Well, there are 2 particular things to consider when you're talking about a percentage being between 2 numbers of some interval. The empirical rule, the previous problem, because it was bell-shaped. Here we're told nothing. We're not told anything about the distribution. So this tells us we have to use Chevyshev's formula. And that means that at least 1 minus 1 over k squared is that percentage, where k is the number of standard deviations you are away from the mean. So here is the mean in between, 51,000. If you look at the difference between 67 and 51,000, you see that difference is 16,000. Likewise, in the other direction, it's 16,000. If we divide this by 8,000, it tells us that we are 2 standard deviations away from the mean. And since we are 2 standard deviations away from the mean, then we know at least 1 minus 1 over 4, which is 3/4, which is 75%. So at least 75% of your data is going to be between those 2 points. Moving on to the next problem. In a recent survey, 96 people were asked if they thought women in the armed forces should be permitted to participate in combat. And we have the results of that survey in this table given here. So we had a total of 96 people interviewed. And our first question, we want the probability a respondent was a male or respondent answered no. So you want the probability that you're a male or they said no. This basic definition of probability, if you have it, is the number of ways it can happen divided by the number of ways anything can happen. Now this is an OR too, so there's a formula for OR. The formula for OR is the probability you're a male plus the probability you said no minus the probability of both male and you said no. Well, the probability you're a male, there are 39 males out of 96. The number that said no was 60 out of 96. And those that are males and they said no, 6 divided by 96. When you add all this up, you get 93 divided by 96. And you may have to reduce the lowest terms. I'm not going to do that, or you might have to express the answer in decimal form. You never know on a final exam. All right? So again, I just used the formula for OR, which is add them together, subtract the probability of both of them happening. Okay? And then the basic definition of probability. For B, we want the probability the respondent was a male and they answered no. Well, that's right here. We already took care of that. 6 over 96. So moving on to the next problem. Okay, this problem here I am going to skip for now because I'm not going to spend the whole time illustrating this to you. It's just going to be too long and too messy. But again, you're going to be basically working with the mean is the sum of the probability of x happening times x. So you just multiply each x to its probability, add them up. And then the variance, sigma squared, is you add up, you take the difference between x and the mean, you square it, and then you multiply it by its associated probability. I usually make a table for that. But again, I'm going to skip this. I might try to add it into the answer page later on. So I'm going to move on though, because that's a very messy problem. And I would be saving that problem for the end of the exam. Alright, next problem. Each month, a household generates an average of 28 pounds of garbage. The standard deviation is 2 pounds, so this is what we're told. Mu is equal to 28. Our standard deviation is 2. A household is selected at random, and we want to know the probability that it is generating between 23 and 30 pounds of garbage each month. We are assuming it is normally distributed. So therefore, we can use the standard normal distribution to determine the answer to this by using the conversion factor, taking x minus the mean and divided by the standard deviation. In other words, this is the probability of 23 minus 28 divided by 2. This is going to be a z now. And then 30 minus 28 divided by 2. You get the probability that you're between minus 2.5 and 1. We'll look these two values up in the z table. I'm going to leave that up to you. For 1, the probability of being below 1 is 0.8413. The probability of being below minus 2.5 is 0.006. This is a scenario where we're between two numbers, so if we're between two numbers, we take the difference between the highest and the lowest. And that answer comes out to be 0.8351. Alright, so again, basically this is a simple probability problem, right? And you know it's approximately normally distributed. Then once you use the z table. Moving on. A survey found that 25% of pet owners had their pets bathed professionally rather than doing it themselves. 15 pet owners were randomly selected, and we want to determine the probability that at most 6 had their pets bathed professionally. This is a binomial problem. You have two outcomes. Either they did get bathed professionally or they did not. So, From the problem, we know we're going to need n, which is the sample size. We need to know the probability of success, and the probability of success here is 0.25. So Q has to be 1 minus that, so 0.75. Now, this is what we're looking for. The probability that at most 6, right? I told you if you have a binomial and it's inequality, if you want to, you can convert this to your standard normal. That is, I am going to solve this. X less than or equal to. Now I want to include 6, right? I want to be below 6, but I want to include it. So if I want to include the 6, I'm going to have to include 6.5, right? Again, here's 6. I want to be below it. So to include 6, I have to go up a half a unit. Next step is I need to convert this to standard normal. I need to know the mean. The mean associated with a binomial is n times p. If you multiply n times p, you get 3.75. The standard deviation is the square root of npq. If you multiply npq and take the square root, you're going to get 1.677. Now we can use this to convert to the z table. 6.5 minus 3.75 divided by the standard deviation. Oh, and square root of npq. Hold on for 1 second. Okay, so anyway, this is, I'm going to say something in a minute here. Z less than or equal to 1.64. And when you look this up in the table, and this is the way the table works, you get 0.9495. In my answer page, I have a 1. I messed up on the calculation here, and I caught myself. So that is incorrect on the answer page, and I might try to fix it. But anyway, the answer to this particular problem is 94.95%. All right, anyway, let's move on. An educator claims that the average salary of a substitute teacher in a school district in a particular county is not $60 per day. A random sample of 8 school districts is selected and the daily salaries are shown. But actually I modified this because I did the work for you. We're going to take the sample mean to be 57 and S to be 3. So you can kind of ignore this because I changed the problem so you didn't have to work with the data because you're not going to have to do that on the final. But anyway, we want to test that the educator is claiming that the average salary in a particular county is not $60 per day. In other words, this is a hypothesis test. H0 is the mean is 60. Because again, H0 is always the status quo. The educator is claiming that mu is not 60. It is different. So that's the first step in the hypothesis test. The second step is the test value. The test value here is going to be x bar minus the mean associated with the null hypothesis divided by, well, we do not know the population standard deviation. We know what the sample standard deviation is, right? So we're going to be working with s divided by the square root of n. Taking this and plugging everything in, we're going to have 57 minus the mean divided by the standard deviation divided by the square root of n, which is, I believe, 8. Somewhere in here. Oh, yeah, 8. Okay? When you calculate this, you're going to get negative 2.828. That's your test value. Now I'm going to move over here. Now I got to decide on the rejection region, the critical region. Well, again, here's the mean, and we're working with the alternative hypothesis that it is not 60. So if we're far enough below or we're far enough above, we're going to reject. So we're going to reject either way up here or way down here. So what is the t-value here? Well, we're going to have to work with the t-table. Alpha is equal to 0.05. It is a two-tailed test. So if you go to the table and you look up alpha for a two-tailed test, the degrees of freedom, we need that. Let me remind you what that is. The degrees of freedom is going to be one less than the sample size, so the degrees of freedom is 7. When you look this up in the table, you're going to get t is equal to 2.365 from the table. So over here, it's a negative 2.365. Since this value here lies in this rejection region, we are going to reject. We will be rejecting the null hypothesis in favor of the alternative at a level of 0.05. Okay? That is as a 5% chance that we are going to make a type 1 error and reject it when it's actually true that there is no difference. All right? Moving on. Moving on to the next problem. 6% of all calculators are defective. We want to find the mean, variance, and standard deviation associated with a lot of 100 calculators. This is the binomial. Either they're defective or they're not defective. N here is equal to 100. P is 0.06. Q is then going to be 0.94, right? So the mean is the sample size times P, which comes out to be 6. The variance is NPQ, which comes out to be 5.64. And you take the standard deviation by taking the square root of this, right? And so you get 2.375 or something in that neighborhood. All right, moving on. A biologist estimates that 30% of the deer in a region contains a particular type of tick. We're taking a sample of 200 deer, and we want the probability that fewer than 50 deer have this tick. Okay, again, this is binomial. P here is going to be 0.3. So Q is going to be 0.7. Once again, this is an inequality associated with a binomial. I'm going to convert this to a standard normal. So I want to be below 50. Since I want to be below 50, I'm going to go to 49.5. I'm going to need to know the mean. Show yourself that the mean for a binomial, again, 60. Sigma here turns out to be 6.481. I convert this to standard normal. I hope I'm going to double check this one because I made a mistake on the last one. So I'm going to double check it. 49.5 minus 50 divided by the standard deviation. And let me see what this comes out to be. And okay, I'm good here, except this is a 60. I caught myself there. All right, this comes out to be a negative 1.6202. And again, if you look it up in the Z table, you're going to get an answer which is about 5.26%. Okay? That's your answer. All right, moving on. And then I'm going to stop here and then create a second video, part 2. All right, let's see. This problem. Advertiser wished to estimate the average price in dollar for a one-day resort pass. The standard deviation from a previous study is $5.31. A sample of 32 resorts found a mean of $50. and we want a 99% confidence interval for the mean price of a one-day resort pass. In other words, we're trying to find an interval for which 99% of the data falls in that interval, right? Okay? Now, since we have a sample of 32, we can use the confidence interval formula, x bar plus or minus z. We have the population standard deviation. Okay, this is one that's really not that clear about, but we do have the population standard deviation of 5.131, and so this is why we can use this formula here. Okay, this is one of these poorly written problems from the book, and but that is the population standard deviation. N is 32. We found the sample mean to be 50, and we want a 90% confidence interval. Alright, so if you take x bar plus or minus z, in this case here, z associated with a 99% confidence interval, z is going to be equal to 2.576. So if you calculate z sigma divided by the square root of n, you come out with 2.4181. If you add and subtract this from the mean, you're going to get the interval 47.58 to 52.42. But the important thing here is you're looking for a confidence interval. Now, it's a sample of size 32, so it's either going to be the t-table or the z-table. Since we do know the population standard deviation, we're going with z here. Okay? Anyway, I'm going to stop the video here. There'll be another video available for the second half.